Okay, we're back for Advent of Code Day 10, but before I get started, I want to show you my view out of this window. I love Bangkok. Anyway, time to sit back to it and do Day 10 of Advent of Code. So let's just jump straight in here and take a look at what Day 10 has got to offer us. Okay. Right, let's read through this and figure out what we need to do. Hopefully it's not too bad. You all arrive at a lava production facility on a floating island in the sky. I'm not reading this stuff. It's all topological map of the surrounding area. Perhaps killed a mosquito. The reindeer is on the book Lava Island Hiking Guide. However, when you open the book, you discover most of it has been destroyed. Okay, you're about to. There's a lot of catastrophes and stuff that happens in these Advent of Code challenges. I think someone needs to go and take a look at what's going on down there because everything's going wrong. The reindeer brings you a blank topographic map of the surrounding area, your puzzle input, and looks at you excitedly. Perhaps you can help. The topographic map indicates the height at each position using a scale from 0 to 9. For example, so I guess lowest to highest. Okay. Based on unscorched scraps of the book, you determine that a good hiking trail is as long as possible and has an even gradual uphill slope. For all practical purposes, this means that a hiking trail is any path that starts at height 0 and ends at 9. So any pattern 0 to 9. And always increases of only 1. Okay, hiking trails never include diagonal steps, only up, down, left, right. Okay, so this is going to be moving around on a grid again. You look up from the map and notice the reindeer has helpfully begun. Okay, another concept, trailhead. A trailhead is any position that starts one or more hiking trails. Here, these positions will always have a height 0. Assembling more fragments of the pages, you establish that a trailhead score is a number of 9 height positions reachable from that trailhead via a hiking trail. In the above example, the single trail head in the top left corner has a score of 1. In the above example, so the single trailhead in the top left, because there's only 1 0, so there's a single 1, okay, and it has a score of 1 because it can reach a 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, okay. There's 2 paths, so you can go this way, you can go that way. 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, there's lots of ways. Okay. But it has a score of 1 because it can only reach 1 at 9, so it's about that position of that final 9. Okay, this trail had a score of 2. I see. So it can go that way or it can go that way. There's only only one way to go in either direction, but they're both different 9s. So it's 2. Okay. The position marked dot are impassable tiles to simplify these examples. They don't appear on your actual map. What is on our actual map? Okay. Let's carry on reading. So where were we? This trailhead has a score of 4 because every 9 is reachable via a hiking trail except the one immediately to the left of the trailhead. So 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it's got 4. I trust it. This topographic map contains 2 trailheads. The trailhead at the top has a score of 1, while the trailhead at the bottom has a score of 2. This is just basically following every single path that can be found from a 0 to a 9, right? Without diagonals. And then here's a bigger example. 9. This has 9 trailheads. Considering the trailheads in reading order, they have a score of 5, meaning so the first one can reach 5 different 9s. Adding these scores together, the sum of order is 36. What do we need to? What is the sum of the scores of all trailheads for your map? Okay, so we need to read this as a numerical grid and search every possible combination from 0 to 9, but it has to go up by 1 each time. And the challenging part's going to be the fact that, so if we take that first 0, we need to look like in every direction, going every direction. We need to like, so there's going to be a directional search from every single 0, not from every digit because trails can only start at 0. From every digit, we're going to do a directional search, but then we have to keep doing that search until we get to a 9, and it can change direction. So like 0, 1, 2, yeah, that goes right. There is a 3. See, this is what I'm doing in my head. I'm like, is there a 3 around there? Yeah, there is. So we go down. Is there a 4? Yeah, there is. So we go across. But there could be 2. At that 4, there's a 5 there. At the 5, there's a 6 there. Oh, but there's a 6 below as well. So you need like 2 threads basically following this. That one and then this one, and then I get 7, 8, and actually so that is like a path that diverges at that 5 there. We can go 6, 7, 8, 9. We can go 6, 7, 8, 9. Go 6, 7, 8, 9 there. Oh god. Okay. This is recursive then. This is recursive. Okay. They had to be recursion at some point. Right. All right. Let's figure this one on the fly. Deno init AOC 10. I can't believe we're at 10. Let's go into AOC 10. I want a run file. I want an input.txt. I want an executable permission. I'll never type it right. Never. There'll never be a day where I type it right. We want a permission on that, and then let's jump into here. We don't want the stuff in here. Inside run here, I'm going to want bin bash deno allow read main.ts. No, don't kill it. Sometimes input.txt main. Let's get rid of that. Let's just write out what we always do, which is context is awaits deno.read text file for import.txt. Let's just check that that's worked. We don't have any input right now, so I'm going to use their input to begin with, because that input is much smaller than this one. So I figure if we print that out, it's going to be hard to see it. Well, actually, this is a test case. I'm not going to write tests, but if we can make this produce 36, then it will produce the other one. But helpfully, we've got some additional information here that we can use when we do this. So I'm going to use their input for now. So I'm going to make all the logs a little bit smaller. Okay. So let's open up a new tab and let's run the script. Yeah. Okay. We need that as a numerical grid, don't we? So we'll go grid, and then that's going to be we split the new lines. Split on new line. We get rid of the last one like we've done in all the other videos. That's not going to be quite what we want though, is it? Because they're still going to be strings. Well, yeah, they're still strings. We need to map each line onto line.split on the character, and then we can put it into characters. Yeah, there we go. And then we need them as numbers. So if we let's map them again and parse int that value. Okay, that's better. So now we've got a grid. We've got the rows and the columns of the numbers in between. Okay. All of this process, this recursion that we need to do, which is to take every digit and then recursively say, go search in every direction for anything that matches the criteria, which is going to be that it's the one of the ones at some location on the compass is one away from the current one. To do that, we need to go from the zeros. We need to start with the zeros. So in this puzzle input, we want to start a recursive search from there, but not from every digit. So yeah, I'm just going to do a basic loop. I'm sticking to basic imperative stuff while I'm thinking. It's not about writing clean code. It's just about solving the problem. Grid.length. Is this right? Let's actually rename that to y, because oops, I don't want IY. I just want y. Okay, and then we want another one of those inside, of course, for oops, what am I doing for? Right, we want, that's going to be x, and then we're going to do the same. We're going to do the same there and there. I'm iterating over this in the way that it's structured, right, because it's rows first and then columns, so that's yn, it's a yx iteration. And then let's just identify now whether those we get the right ones. So that's going to be like grid yx. If grid yx is equal to 0, we can deal with numbers now. Then let's just log yx. Okay, so 3, 4, 5, 6, 7, 8, 9 cases of a 0 in that input. Is that what we see? There's one there. There's two on the first line, then 3, nothing there. 4, 5, 6, 7, 8, 9. Yeah, okay. Okay, so we've got those coordinates there, and then what do we need to do now to know? We're trying to find how many paths go through to a unique 9. If we keep the path, we don't need to know if it's a unique 9. If we just iterate, if we recursively go through every single one of these things. Yeah, I feel like we need to have some kind of like if we have some kind of search here, and the search, that's going to call itself, and it's going to search from y and x because we've just found that there's a 0 there. And if that's recursive, it needs to add, it needs some initial value, which is the paths that it can pass back to itself. That's how recursion. If you've never used recursion before, if you're a newer engineer, it bends your brain a little bit. Recursion, there's a function that calls itself, and it continues to call itself, passing usually something into itself again and again that it builds up, kind of like a reduce works in reverse. And it needs an exit condition at some point. The exit condition, otherwise it will just blow the stack. In fact, it can still blow the stack even if it has an exit condition, because it might just get too big, because the function calls itself, and then as part of function f calls f, you've actually got to unroll all of those back. So some languages can optimize that. It's called tail call optimization. JavaScript doesn't do that, or at least I don't think it does that. Plus it can only do it in a tail call position. I don't think we're going to do that here. We're not going to use tail call recursion anyway. So, but I can see already that like the input grid is not big enough that we're going to blow the stack here, but we do need to make sure we exit properly. And the exit condition, if we take every digit and we say just keep searching from that digit, keep searching from that digit, add the path to the memo that's happening between them, then when you reach a 9, then you've got a complete path. So then you can then add that to some, I don't know, some kind of other more global variable that contains a list of paths. So yeah, we're going to be building up a list of paths. I'm completely opting out of TypeScript right now. Let's just leave that as any for a second. It's going to complain at me. That's what that. Oops. That's what this over here is, that any is not allowed, but I don't care. It's not an error. It's just a complaint. It's complaining that search doesn't exist because it doesn't. Let's just create that for a second. So we're going to say y is a number, x is a number, and path. That's the individual path that it builds up each time. So that needs to be, it's going to be every coordinate that it finds that it continues on. So it's an array of objects that contain a y and an x. Yeah. Okay. Let me just, I know I said I was opting out of TypeScript here, but I just feel like that should be like, let me call that type yx is, y is a number, x is a number. I want to type it because otherwise that signature is too big. And so the path is a yx array. Right, this is the search function. And so the purpose of the search function is to take a y, take an x, and then recursively search the grid from that position, looking for the exit condition. What's the exit condition? So let's just take the current value that we find at grid yx, because that's the one that we're looking at right now. So in the first case, that's going to be 0, which is fine. But if the current value is equal to 9, then we're done. We want to get out of this iteration. Otherwise, we need to kick off a search in every direction. So we need directions. Okay. Let's create an array of directions that contain, like, we've kind of done this in previous videos as well, actually. It's like a dy and a dx, which is the delta from y and x. If we say, let's do CSS, up, right, down, and left. So up is -1, let's not get this wrong, because we got this wrong last time. Although if I get another mistake, I'll be coming here straight for it. So we're going to go, that's up, and then we're going to say up, right, which is 1 on x, up, right, then down, which is 1 on y and none on x, and then left, which is nothing on y and -1 on x. So, okay, so those are the 4 distinct positions. Cursory glance over those looks right. We don't see any duplication there. So, we're gonna search through that stuff. Let me just stick a console log for paths there, because right now, if I run this code, nothing's gonna happen. But we want this search function, which is gonna call itself in a second. It's gonna build up paths. So I'm gonna log paths after this stuff here. All right. Right. How do we go off in all directions? We need to loop through those directions. Again, doing this very imperatively. Dirs.length i++. So now we can access each dir I, and that tells us. Okay, so let's calculate like a new y and a new x. And so a new y is going to be the direction in question dot dy. No, kind of. It's going to be whatever y currently is plus that thing, and then it's going to be x plus whatever the current direction is dot dx. So we've got 2 new coordinates, and we're going to do that for every direction. So we're going to generate 4 sets of new coordinates for every single yx that we get given here. And then we need to go search it, but only if, okay, there's several conditions. Only if we only want to go and search that other digit if it's 1 or more than the current one, because if it's not, then it's a dead end. We also only want to search it if it's possible, if it's in the bounds of the grid. So let's do the bounds check. So ny needs to be greater than or equal to 0, otherwise it's minus, it's off the top of the grid. And ny needs to be less than, so 0 base index, so it needs to be less than grid dot length. And then x needs to be also greater than or equal to 0, and then nx needs to be less than, well, if it's a square grid, we can just do that, but let's do grid 0 dot length. Although I suppose that's kind of assuming the same thing. Well, it's assuming that it's not like multivariable. I mean, I already know, right? Let me just take a look. Oh, let me take a look at the actual puzzle import. They're all clearly the same length, so I don't actually need to do anything special there. Let's just leave it simple. Grid dot length, because we know that's going to be fine. If it's in the range of the grid, okay, Wow, there's lots of numbers in this. I'm getting a bit confused here. We figured out whether those new coordinates are actually inside the grid or not. What we've not figured out is whether the thing at those coordinates is one more than the current value. Because if it's not, then we do not care. So what we need to say here is if grid new y new x, if that value is equal to the current value plus 1, then we want to go and search at that location. So here comes the iteration, the recursion, sorry. So we're going to search at new y and new x, and we need to give it whatever path we've... See, this is the hard thing about recursion. You've got to... in recursion, my brain tends to just think about iteration 0, but this could be iteration, I don't know, 50,000. We have a path, an array, a path here that's currently got values inside it, and we need to not only give it the same one back so we can keep adding to it, but we need to add to it at some point as well. So we only want to add to it once we know that the path is like correct, which we've only just discovered now. So this is one of those really nice things in JavaScript since this addition of this spread parameters come out. So we can say create a new array and take all the values from path and put them on this array first. That basically takes an array and then like breaks it out into multiple values. So this would be the same as being like path 0, path 1, and so on for however many there are in there. So we can just say we're building up a new array called path. Sorry, we're building up a new array. It's not called anything, but we're taking out the values that we've currently got from path, and then we need to add another one to it. Let me just... Yeah, okay, just making sure the TypeScript signature works there. So we want to say the path, yeah, that's actually y and x. It's not ny and nx. Ny is the new one. The new one might not. The new one will get added next time. So it's y and x. Okay, and what's going on here? Cannot find dir. Oh, yes, dirs. Sorry. Right. Okay. What does this do if I run it? Nothing. Oh, okay, yeah, of course. That's because when we exit this function, when we finally find if we don't find a 9, it's no problem. It doesn't do anything to paths. That's what we want to happen. But if it does find one, then we're going to need to say paths.push and stick on the current path. Yeah, I think so. There we go. I mean, it looks right. Maybe. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. 0 to 9 is 10 though. I want to see the number in here that we're looking at each time to see whether we're actually doing the correct thing or not. So when I add to this path, when we add this path variable here, if we stick on whatever's in current, no, can't do that. Oh yeah, I can do that if I do this. Okay, we're missing one. It is counting upwards though, so this is looking promising, but it's missing the last one. Missing the last one. Why? If it's current plus 1, yeah, I see. Because we add the y and the x here, then we search the ny. If the ny ends up producing 9, we push it off. So we kind of need to do the same thing here. We need to, let's just literally do exactly the same thing as we did below, which is going to be y, x, and v, which is current. I think that'll give us the one. There we are. So we got 0 all the way through to 9, and coordinates. Let's just take that last one as an example. y7, x1. If we look in this input, y7, so 0, 1, 2, 3, 4, 5, 6, 7, and 1, which is 0, 1. So that is a 0. So that's the correct first coordinate. That coordinate is the correct coordinate 0. And then do we find, at 5, 4, do we find a 9? So at 5, 4, 0, 1, 0, 1, 2, 3, 4, 5. What was it? 5 and 4, 0, 1, 2, 3, 4, and 9. Yeah, okay. Presumably the other ones in the middle of that produce a path to it. but that that seems to work. How many do we get? How many do we get from there? 1. So in their example, they mention 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 paths with a score. Yeah, okay. Right, so we have a lot more here, but I've not written any code at all, any special code here at all to make sure that we don't if it ends up at the same 9, it was in that example, it was 5 because starting at 0 ended up at the same 9. There's 5 ways to get to that 9. Or rather, that 9 can be found 5 ways. But here we're just finding any combination of 9s, any path for 9. What we really want to know is for this starting position 0, how many of them actually end up at the same 9? 3, 4, I'm trying to see if there's examples in the data. 0, 9, 3, 9, 4, 9, 2, 9. Ah, there we go. There we go. So that one starts at 6, 6, and it's a 0. That one, and it's the same 0 here. And then, we end up at 2, 5, and 2, 5. Now somewhere in the middle, there's a different path. There we go, because the second to last coordinate, 3, 5, is actually 1, 5 here. So there are 2 paths here going from the same 0 to the same 9 that are different paths. It's found 2 different paths here. So that would count as a score of 2. But then this one would not count. So we need to count the number of coordinates that start this way and the ones that end this way. And there's going to be some that end at the same 9, so they don't... No, there are going to be some that start with the same coordinate but end up at a different 9, and that doesn't count, I think. We need to come out with 36, not 81, but we've not done the sum yet. So if we use, I'm thinking if we create a map and we use the first coordinate pair as a key, and then for every, let me think about this for a second. We need to calculate all of those. So yeah, I need to see this data again. If we use this as an index here to a map, then we can say that's one of the zeros, that's a starting 0. And if this means we found a 9, but we don't know it was the same 9 as a different one. So if we use that as a map and then the key is another map, yeah, the key needs to be another map, because if we produce the same 9 again, then it doesn't count. It's only when there are unique paths to a 9. Let me just look at this again. This is a score of 2 because that 0 gets to 2 different 9s. Right, okay, so I was thinking about it the other way around. A score is that this 0 can find 2 unique 9s. If it was to find the same one via different paths, that would not score. That would be a 1, which is what this example was, because there we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, and we can go 1, 2, 3, 4, 5, 6, 7, 8, 9. We can go 0, 1, 2, 3. Yeah, I think that was different. But either way, that has a score of 1, it says. Where does it say that? Somewhere it said that the score for that was 1. In the above example, the single trailhead in the top left corner has a score of 1 because it can reach a single 9, the one in the bottom left. Yeah, okay. Alright, okay, so this is making a bit more sense now. So yeah, if we create a map then, and we say that the first, well, it's a map of a map, That way we can just overwrite the duplicates because we don't care about those. We only care about when they end up at a different 9. So that feels like it will work. So I'm just going to call this map, and I'm literally like, TypeScript can get to hell because I'm going to do crazy stuff and I don't care. I know in this case I don't care about the typing as much anyway, because I'm also I know I'm looking for the answer 36, was it? I know I'm looking for the answer 36 because I'm using their input. Hopefully our input, the real input, doesn't have some kind of like weird problem in it that makes it harder. Right, okay, so what do I need to do now? I need to go through... We need to go through everything in, what's it called, paths. See, if I did have type information, I'd know what this was structured like without having to think about it in my brain. But, you know, I did the difficult thing, and now I'm stuck with no types. Path.for each path, so we'll go through every single path that we've got, and then a path in this case is something that we pushed onto it there, which is another array containing, well, x, y, and v actually right now. Yeah, I'm not going to take that v out, I'll leave it there. So it contains x, y, and v. Let me just make sure we've got the right stuff here. So path, like what? Path 0 and path dot length minus 1. I'm just trying to, no, that's not going to work. Why not? Oh, it's that that's the problem, sorry. Path has implicitly an any type. Yes, it does, because I'm making my life worse. Leave me alone, let me do it. yxv, yxv. Right, they're all... Yeah, okay, that makes sense. They're the 0. I'm glad I left the v in there now because it makes it easier to see this. So those are the ones on the first one and the second one. Alright, so let me see. What I need to do here is say that if the map doesn't contain a value, no, what am I doing? If the map does not contain a value for what? For the first path coordinate, because I need a map of maps, so I need to initialize this to be a map of maps. So it's getting confusing. If it doesn't have... Right, hold on a second. I need keys. I can't write this in one big go. It's going to be really messy. So let's call it like the... I'm going to call it absolutely bankrupt in terms of creativity of naming today. I'm going to call it first key and second key. And meaning... Or I'll call it last key. Because the first key is going to be... The first key is going to be path, and I want the first element of path, and I want its y, and then I want path first element, and I want its x. That's the first one. It's the first coordinate of the 0. And then we want path, we want the last one. If only there was a dot last. Actually, is there a dot last? Last key, no. Right, and that's going to be y, but here it's going to be path dot length minus 1. And then that's going to be, again, the same path dot length minus 1 dot x. Right, let me just get rid of this for a second and just see if those keys make sense. First key and last key. Yeah, there we go, pretty much what we just had. 7154 at the end. 7154, okay, good. Because I want to use, I need to use those keys to index this map. I need to say, I can now say if not map first key, then let me just initialize that by saying map first key is equal to an empty map. And then what we can do is we can always simply say map first key equals a map of where second key is what? True. I don't care. I just need to put a value in there. And then let me see what's inside map. That's wrong. Why is that wrong? Cannot find second key. It's called class key. Nice. Okay, so because we've put them in maps of maps, all of these values that are the same, that override each other, don't obviously just override the same value in the map, and we don't get them. And so what we actually have here is like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 values, which I think in their import, yeah, they had 9 values as well. Right. That's good, I think. But how do we calculate the scores? How do we calculate the scores there? The old grease cells figure this one out. So we need to produce that 5, 5. Yeah, this doesn't look like the right value. This doesn't look like the right value to me, because we're saying for every first coordinate, we're taking the first coordinate and we're taking the last coordinate of that map, and then what we're trying to say, have I still got the map on the screen from up here? This one. Yes, we're trying to say that do they produce, does the same one produce a different 9? Yeah. But in this map, it doesn't produce that. I think I've just done the wrong thing altogether here, which is, that's what we wanted to do. Yeah, I was, for some reason I wrote it like this. What am I doing? I'm overriding the first key with this thing. That's not what I wanted to do. I want to say, now that we've initialized this map with the first key, we want to put the last one in there. So we're going to say index it to the first one, which is the first one, index it to the second one, which is either the same. If it's the same, we override it, no problem. If it's not the same, we add a new one. We add a new second key, basically, in there. Okay, that's more like it. And this is looking, let me clear the screen again so it's a bit more easy to read. So here we got 1, 2, 3, 4, 5, and then 1, 2, 3, 6, and then 5 and 4. So 5, 6, 5, 4. Is that what they've got there? 5, 6, 5, 3. 3. I'm sorry, it is 3, not 4. I counted it wrong. Thank God. Okay, so it looks like we're going to produce the same, maybe the same value as they are now. What we actually need to do is just sum up those lengths. Yeah, so I can produce, let's try and produce that number now, and hopefully it will be 36. Okay, so we can say object.values from map, and that'll give us everything on the right hand side, all of these values here. And then nothing fancy today, console.log, whoa, let's try that again, console.log sum, and then here if we take the values and we of the map, and then we want to go through each of them, now the values Oh, the values is another map. Okay. So we'll say the value is another map, and so we'll say that sum is plus equal to object dot. Well, it doesn't matter whether we say values or keys at this point. Of v dot length. I'm doing some very weird. What's this? No overload matches this call. Really. Is it just because I'm doing it in one line like an idiot? Probably is. Let's just do this here. So object sum is plus equal to object dot values of v dot length. Object dot values gives us back an array like of v, because v is each map here. What is in v? What are we actually even looking at there? Yeah, it's all of these values here. That's an object dot value should give me all the trues, right? Object dot values of v. It does give me all the trues. What's this complaining about? No overload matches this call. That's strange. I'll figure that out at a different time, but it seems like TypeScript is giving me the wrong information there. Let's put that back. So I was right all along then. Sum plus equals that, and then we had to do an extra one at the end there. None. Okay, maybe they, oh no. Plus equals. And then dot length. Really fumbling the way to the solution here. There we go, 36. Okay. It's quite interesting that TypeScript thinks there's an actual error there. But anyway, it doesn't matter, I don't care about that, there's not. And this is what happens when you just opt out of type safety, you end up with all kinds of weird things that you can't explain. So let me grab the real puzzle input here. And, 1 second. Grab the real puzzle input and copy that into here. Save. Let's jump back over here and run it. 798. Is that the right answer? 798. Hey, there we go. Finally. Okay, quick review. This was a very imperative solution. Code's not very nice, but it's definitely approached this one of like, let's just solve. Wow, I'm very dark now. Apologies for that. 1 second, let me turn my light on. That's a bit better. It went dark in the time that we solved this one. Yeah, code's not very pretty, but I think this is a pretty straightforward solution. And the key there is this recursion that's happening here on this line. So yeah, that's it. That's what this challenge was all about. It was about pathfinding from a location in every number of possible different directions, and then later like applying that rule to it, that it's only when it finds different nines that it counts as a score. So interesting one. It was a little bit more of a challenge, I think. If you didn't see the recursive solution, it probably would have been quite messy to do that in some kind of iterative loop-based way. But again, if you've got a much simpler solution or there's something I missed, let me know in the comments. And yeah, let's see what tomorrow holds. Day 11. I'll see you then.